Welcome students, and in this video we are going to continue our study with that Lyapunov stability. So last video we have looked at some Lyapunov stability, right? So when it is stable and all that sort of thing. Now the thing is here what we are going to do is, first of all I am going to start with the definition, and then I am going to explain in the context of the definition what we did in the last video. So definition. So this definition is of something called a equilibrium point or a critical point. Definition. So what is it? It says that a point B star in Rn is called an equilibrium point. Okay, for an OD. What is the OD? X prime equals to f of x. Is it okay? If f of B star is going to be 0. Is it okay? So basically at that point, if capital F, the source term, that is basically 0, then we call this as an equilibrium point. So essentially what is happening is this: see, if f of B star is 0 at that point, so x prime at that point is basically 0. That's what it is saying, right? And at that particular point, we will call it as an equilibrium point for this system. So let's look at some example. Let's say as an example, x prime equals to ax. This is a linear system, right? Linear system, constant coefficient, of course, linear system. Now you see what is f of x here. F of x is ax, yeah. And for now, let's just assume that a is invertible. It doesn't have to be, but let's just assume this, huh? A is invertible. So if this is the case here, then where you see, basically if we want to find what are the equilibrium points, we have to say that when is ax equals to 0. Since a is invertible, that will only imply x has to be equals to 0. See, irrespective of a is invertible or not, x equals to 0 is always the equilibrium point. So irrespective, let me put it this way: irrespective of a invertible or not, okay, x equals to 0 is always an equilibrium point. I hope this is clear. Equilibrium point. Okay, see, if a is invertible, then this system has a unique equilibrium point. If a is not invertible, it has I mean, of course 0 is an invertible point, but 0 is an equilibrium point, but along with that there are other points also. Okay, that's the thing. Now for non-linear system, it may happen that 0 is not an equilibrium point, or maybe, yeah, it differs. So for non-linear system, this is definitely, there can be points other than 0. It can be 0 also. It may happen that there are no equilibrium point which is 0. So basically anything can be equilibrium point. Okay, so let's look at one example. Let's say that the thing x prime equals to y and y prime equals to x minus x cube minus beta y. Okay, beta y. So this is and here we are assuming that beta is positive. Okay, so this sort of equation, this is called Duffing's equation. Okay, and for this equation, what you can do is you can actually show, you see, what is f of xy in this case? It is x minus x cube minus beta y. Okay, now if we evaluate, of course x has to be 0. So the any equilibrium, for any equilibrium point to work, see, it is 0 0, right? So x equals to 0, and then you have to evaluate y. So essentially this has equilibrium point, if you just calculate this thing, point 0 0, and also plus minus 1 0. Okay, so there are 3 equilibrium points for this system. Is it okay? So that's the idea. Now let us discuss what exactly is so important about equilibrium point. See, essentially, let's say that so if B star is an equilibrium point, let's just assume that that B star is an, I am writing it like this, EQ point, equilibrium point of x prime equals to f of x. Now B star is what? B star is a point, right? It's some a vector in Rn, right? Now note this, that if I am defining a new function x of t, which is a constant function given by B star. Is it okay? So x of t is a constant which is B star everywhere for all t in R. Now you see what happens to x prime t. Therefore, x prime of t is going to be, it is constant, right? B star. So that is 0, which is nothing but f of 0 is nothing but f of B star, right? Okay, so you see, if B star is an equilibrium point, then the function B star, so B star as a point is an equilibrium point, but if you can think of it as a function, so basically it's just a constant function, and that also solves the equation. So that is always a solution of the equation, that is always there. So if you can find the equilibrium point, okay, so and if we define a solution out of it using the constant this thing idea that the function is constant, then what happens is that function also satisfies the equation. Yes. So what is happening is this. See, let's say that it is saying that now for this thing, let's say as I mean, if you have a function like this, x at the point t is B star, right? So in that case, x at the point 0 will also be B star. So essentially what you are saying is this. Let's say at the point t equals to 0, this is B star, B star. So what it is saying is this. Let's say, see this equation, x prime equals to f of x. Now look at this equation, x0 equals to B star, and B star is the equilibrium point, and B star is the equilibrium point. Okay, let's look at this thing. See what it is saying is this. The first thing, x prime equals to f of x. What it is saying? It is talking about the rule according to which the particle moves. Is it okay? A particle is moving, right? See, a particle in this case, let's say this is in 2 dimension, right? 2 cross 2 system. So basically capital X is nothing but small x and small y. Okay, now capital X is a function of t, so it is basically small x of t and small y of t. Is it okay? Now this particle, it moves, right? So and what is the rule? It is x prime of t. What is it? It is small x prime of t, small y prime of t. So basically it is saying that the tangent is given by the vector field. Okay, now, and what is the x0 equals to B star? It is saying that what is the starting point of the particle. Okay, so where does the particle starts? So in this case, the particle starts with B star. Okay, and what is the solution? The solution is also B star. So basically what it is saying is this: if a particle starts at B star, if a particle starts at B star, it does not move as time moves. So basically it ends up at B star itself. Okay, so that is also a solution. Yes. Yeah, do you understand? So basically why it is equilibrium point? Because it is not moving. If it starts there and it ends up there itself for all time t, it's not moving. Okay, now you see what is Lyapunov stability. Let's say we are saying that a particular solution, yeah, let's say a solution is stable, yeah, around an equilibrium point. If we are saying a solution is stable around, so basically let's say here B star is the equilibrium point, right? So if we are saying it is stable along equilibrium point, what we mean by this is essentially if we start very close to B star, right, stability, you remember, if we start very close to B star, okay, for all time t we will always remain in a close neighborhood of B star. So there is a neighborhood of B star, let's say V, where we are always, the solution will always be contained in that. Is it okay? It cannot, I mean, go out of our neighborhood. So basically there will be a neighborhood where you can contain the whole trajectory of the solution. So basically, see, this is the original solution. So B corresponding to B star. We know that corresponding to B star there is a solution which is given by the B star itself. Okay, and let's say you again look at this problem, x prime equals to f of x, and x at the point 0 is B star, no, but in a very I am taking B and such that B minus B star is extremely small. Is it okay? Very small. So I am choosing a B star from a very, very small neighborhood of this thing, let's say delta of B star. B from a neighborhood of B star. Once I do that, then we get a solution x of t, right? We get a solution, and that solution for all time t, yes, that must be confined in a neighborhood. So you get a epsilon, okay, first of all you fix a epsilon, and for that you get a delta such that what happens is your x of t minus b star should be less than epsilon. Is it okay? So that's the idea. Essentially, you start in the neighborhood of B star and you end up in a neighborhood of B star. Yes? Okay. So the solution will also mimic that. That's the idea. So that is the idea of stability. And what is asymptotic stability? The solution will actually converge towards B star. You understand? It's time stability. So it will spiral into B star. That's the idea. Okay, so that's more or less the what essentially means what we did in the last video. So in this video, what we are going to do is this. See, we looked at some certain criteria under which the linear system is stable, is asymptotically stable, that sort of questions, right? Now in this, what we are going to do is this. See, in the last video, we have seen this. So let me put it this way. In the last video, we showed that for the linear system x prime equals to ax, okay, if the eigenvalues of a okay satisfies the real part of lambda j. So basically it means that the lambda j of a is the eigenvalues of a. If we look at all the eigenvalues, if we look at the real part, let's say that is strictly negative for j equals to 1, 2, what can you say? Then every solution x of t, okay, decays to 0 as t tends to infinity. You remember we talked about this, right? See, x prime equals to a of x, right? And all the eigenvalues. So for a 2 cross 2 system, let's just understand that 2 cross 2 system, you don't have to worry about all these things also. For a 2 cross 2 system, you see, if lambda 1 and lambda 2 are both negative, both are real, let's say, both are real and they are negative, then what is the solution? It is v1 e power lambda 1 t c1 plus c2 times v2 e to the power lambda 2 t. v1 and v2 are the corresponding eigen functions, right? Now you see, if lambda 1 and lambda 2 are going towards 0, what happens to this solution? This solution tends to 0, 0, right? That's what going to happen. So that's what wrote, right? Okay. Now, see, the thing is, now we are going to see linear this thing system is fine. Now the thing is, what happens in a nonlinear system? That's the question which we need to answer. Now see, in the earlier case for the linear system, what is happening is the solution we are talking about, it is going towards 0. As t tends to infinity, the solution is asymptotically stable, and it is basically, while it is moving into 0, right? Yeah, it is spiraling into 0. So, but and what is so special about 0? Because in a linear system, you see 0 is an equilibrium point. Is it okay? That is why. Yes. Now what is happening is this. Let's say if you have a system like x prime equals to f of x. You understand? So now consider the system x prime equals to f of x. Is it okay? And we want to look at the asymptotic behavior of solutions of this system near the equilibrium point B star. You understand? So the question is the asymptotic behavior okay of the solutions near B star. B star. Is it okay? Asymptotic behavior near B star. So what is B star? B star is the equilibrium point. Okay. Now how do we find it? See, so what we are going to do is this. See, the theorem which we are going to prove is the following, and this is a very, very important theorem. Okay. This is part of a stable manifold theorem, so you can also call it stable manifold theorem. It's not a problem. Okay. So what it says is this: suppose B star is an equilibrium point, of x prime equals to f of x. That's our assumption, right? Where what is f? F is C1 of omega. Oh, omega is any open subset of Rn, yeah. And assume that the real part, okay, real part of the eigenvalues. So you look at the eigenvalues of df star. What is df star? So it is basically the derivative of the function f evaluated at b star. Let me write it like b star. Okay. See, f is a C1 function. So df is defined. df at b star is a linear map, right? So basically it's a matrix. Yeah. And we can talk about the eigenvalues of the matrix. So those are the eigenvalues. Let's say lambda j is our eigenvalues. Now look at the real parts of those eigenvalues. If they are negative, okay, for j equals to 1 to n, okay, then what we can say is this. You see, then there is a neighborhood. There is a neighborhood, NBD neighborhood, okay, neighborhood V of B star in Rn, of course, in Rn, such that for any initial data B, okay, in V, is it okay? The initial value problem. What is the initial value problem? X prime equals to f of x and x0 equals to b. Okay, has a solution for all t greater than equals 0, and moreover you can say that limit t tends to infinity x of t is b star. Is it okay? So basically what it is saying is this. See, whatever I just explained here, so let me explain it again here. See, the thing is, let's say that I know that b star is the equilibrium point of this system, f prime equals to f of x. See, b star is the equilibrium point. This is what I am assuming. Okay, now, so b star is the equilibrium point, right? Now let's say v is a neighborhood, and such that you look at df b star. That's a matrix, right? It's a linear transformation from Rn to Rn. Now you look at the real part of that matrix. Okay, sorry, you look at the eigenvalue. Sorry, so that's a matrix. Now look at the eigenvalues of this matrix, lambda j, all the eigenvalues, and then look at the real part. So basically, if they are all real eigenvalues, then real part is the eigenvalue itself. If it is complex, you just look at the real part. If they are negative, okay, then for the linear system, we know that what happens, the solution goes asymptotically towards 0. So basically at the critical point. Here what it is saying is this same sort of thing happens. So basically here it is saying that if this something like this happens, and for a linear system, if you start with a b from a very close to b star, that's what I explained here, right? If you start with a b in a neighborhood of b star, you see v is a neighborhood of b star, and if you take any b from v star, then what happens is the solution starts from here, and for all t there is a solution, okay, and what happens at t tends to infinity, it actually goes towards b star. You see, that's what it is saying. It is saying that if b star is the equilibrium, then there is a neighborhood v of b star in Rn such that for any initial data, so if you are choosing an initial data from v, then what happens is the problem f prime equals to f of x, x0 equals to b. Okay, with that initial data, the solution exists for all time t, and the solution, what is the asymptotic behavior of the solution? It actually converges to b star. Yeah, it is actually very intuitional, if you think about it. Now the thing is, what is the proof? Okay, so you see, what we are going to do is essentially I am going to start with a translation. See, here I started with b star is the equilibrium point. You can also choose it to be 0. It's not a problem, right? So without loss of generality, we assume that the equilibrium point B star is 0. Okay. If it is not 0, you just translate everything in Rn. It's not a problem, right? We can do that. Okay. So what we are going to do is I am going to choose B star to be 0. That's what I am going to do. So basically, I am assuming that the equilibrium is located at origin. Yeah. That is f of 0 is 0. 0 is always there. So that is the equilibrium point definition. And this is B star, right? So this I am choosing it to be 0. Is it okay? Now what I am going to do is, you see, f is a C1 function. It is given f is C1. So I can expand f, right? So basically, you see, f of x in a neighborhood of 0 essentially, yeah? In a neighborhood of 0. What we can do is I can write f of x to be a of x plus r of x. Right? Where a of x is df at 0. Yeah? And r of x is the remainder term. Do you understand what we are doing here? We are using Taylor's theorem here. See, first of all, f of x is f of 0. If you remember, f of x is nothing but f of 0 plus df at the point 0 acting at h, and all those things are there. But see, f of 0 is 0, so this is gone. So f of x is df x acting at df 0 acting at x, right? Okay, so this thing I wrote it here. You see, df 0 acting at x. Is it okay? This is 0. And then you have a remainder term. So this is first order Taylor's theorem. This is what I am using for a variable, several variable functions. Yes, r is the remainder term. Now you see, we know that from the earlier this thing we talked about it, right? That there exists a constant k and epsilon positive such that we can always do this, right? Mod e power. So for this a, I will choose this a and I can write it like this. See, for this a, e power at can be made less than equal a constant times e power minus epsilon t. If you remember, yes, for t greater than equal 0. We talked about this thing, right? This actually holds. While talking about asymptotic behavior of the solutions, we use this fact also, if you remember. Of course, you can do realize k is greater than equal 1. It has to be. That's the by definition, because at 0 also it is 0. So it is 1. So essentially k always has to be greater than equal 1. That's just given. Okay. Now what we are going to do is I am going to do a little technical jargon. I'm just going to write it. So we choose eta positive such that eta is less than epsilon by k. I hope you understand what's the idea of the proof, right? The idea of the proof is very easy. So think about it. Here it is saying that I want to have some sort of property, okay, of a nonlinear system near an equilibrium point. Yes. So for a nonlinear system near an equilibrium point, okay, think about it. Since f is C1 in a neighborhood of the equilibrium point, I can think of the nonlinear system as a linear system. I can approximate it, right? And the behavior of the linear system, I expect it to work also for a nonlinear system. That's what it is happening here. So essentially, this is called the linearization. Okay, this is called linearization. So basically, what I am doing is I am linearizing the original, x prime equals to f of x with this. And then if I do that, what happens is this. Basically, I am not talking about the original, equation anymore, but I am talking about a constant coefficient equation. Okay. Now, let's look at that. So you see, we choose eta greater than 0 such that eta less than epsilon by k. This is just some technical issues. So, and you see that r is there, right? Yes. And what is the property of r? That there is also there exists delta positive such that if norm of x is less than equals to delta, okay, then norm of Rx. You remember the reminder term. This is the reminder term of Taylor expansion. Reminder term, norm of Rx will be dominated by eta times norm of x. Is it okay? That's just the definition of the reminder term, right? Okay, so we can always do that. Okay, now the thing is this. See, what we are going to do is this. So we are going to define a new set V. What is the definition here? This is the set of all those B in Rn such that mod B is less than delta by K. Okay, this is contained in the ball with radius center 0 and radius delta. Why? Because you can see that mod B is less than delta by K, so which is again contained in delta, right? Delta radius ball. Okay, now you see the thing is this problem. Where is the problem? X m equals to f of x, x0 equals to b. Yeah, this problem for f in C1, we have that this problem is not solvable for all t greater than equals 0. You understand what I'm saying? That's just we talked about this theorem, right? That we cannot solve this problem for all t greater than equals 0, right? So if we can't do that, then what does it mean? If we see, the thing is, in the last when we talked about asymptotic stability, when we talked about maximal interval of existence, what did we say? That if there is a solution of this problem, right? So the trajectory, if we can bound the trajectory in a compact set, yes, then what can we say? Then the solution exists for all time t. It has to be, yeah. Otherwise, it can't be. So you cannot trap it in a compact set otherwise. So let's say that if you have a solution which is not solvable, so basically if this problem is not solvable for all t, so basically the trajectory does not exist for all positive t, then the solution of this problem must leave the ball b0 delta bar. You understand? So therefore, if a solution exists for all t in 0 infinity, okay, if a solution does not exist, see, we have to prove it exists, right? It does exist. See, we have to prove it does exist for all time t. So basically what we are assuming is this. Let's say if their solution does not exist for all time t, okay, then you cannot put it in a b0 delta bar, right? Yes, then x of t cannot be contained, the trajectory cannot be contained, does not belongs to b0 delta bar for all t. Yeah, you cannot contain the trajectory for all t. Okay, so essentially what it means is x of t must leave the compact set. Okay, so let me put it this way: x of t must leave b0 delta bar, right? That's what it is. See, this is where we are actually going to find a contradiction. So we are assuming that they say that there is a t star positive such that mod x of t is less than delta, okay, for t less than t star, while mod of x t star equals to delta. Is it okay? So what we are saying is this: let's say there is a t star up till t star. Okay, what happens is for all t less than t star, x of t is within the ball. Okay. Now see, as the solution does not exist for all time t. That's what our assumption is. See, we have to prove it exists for all time t. So we are assuming that let's say it does not exist. So what happens is that in that case it starts from the 0, right? And the thing is, what we are saying is this: it is not contained in that compact set, because if it contains, it has to be it has to be there for all time t. Okay, so it has to leave the compact set. Now if it is leaving the compact set for there is some time t equals to t star where it has to touch the boundary. Okay, it has to touch the boundary, and what is the boundary? At the boundary mod x t star is delta. Okay, of course it has to be, right? Now you see what we are going to do is, so from here we are going to assume get the contradiction. So we are going to define a new function g of t, which is e power epsilon t, the norm of x of t. Yeah, and we will use Gronwall here. Okay, so what we are going to do is, you see that equation, this equation, which is equation x prime equals to f of x, x equals to b. This equation we are going to write it like this. See, let g of t is this, and we rewrite. Okay, see, x prime equals to f of x, and what is f of x? F of x is ax plus rx, right? So we have x prime equals to ax plus r of x. Is it okay? And what is x0? x0 is given to be b. We can rewrite the equation like this. F of x, I am replacing it with x. Yeah. Now you see, this is a linear equation, constant coefficient. Of course, there is the inhomogeneous term given by this. Yeah. So this equation is nothing but, you see, x prime equals to, sorry, this is a linear equation, is constant coefficient. A is constant. Sorry, A is constant, right? Yeah. And what is A is df at the point 0, but A is a constant coefficient equation, it's a linear equation, right? Okay, so we can actually solve this problem. What is the solution? By Duhamel's principle. So therefore, what is x of t? It is e power at times x naught, which is b, plus 0 to t e power a t minus s r of x of s ds. Is it okay? That's what x of t is, right? By Duhamel. If you remember Duhamel's principle. Duhamel. Why? Because in this case, what is the fundamental solution? It is e power at, right? Okay. So now if we multiply this particular equation is e power epsilon t. So multiply by e power epsilon t, one has g of t. Yes. You see, multiply and take the modulus, then take the norm exactly, e power epsilon t, and then e power at times b, the norm of that, plus e power epsilon t, and then 0 to t mod of e power t minus s a r of x of s ds. That's what we are going to get, right? Okay, what I am doing is this particular expression I am just multiplying by e power epsilon t, and I am just taking the modulus, okay, or the norm, that is. Now you see this equation e power at. Yes, what we are going to do is we are going to use the bound on the exponentials. You see, e power at, norm e power at is less than equal k times e power minus epsilon t. Okay, so if you put that, therefore what you have is this g of t is less than equal k times mod b plus k times 0 to t e power epsilon s r of xs ds. Is it okay? Just by using that bound. So you see, therefore for t less than equal t star, see, for t less than equal t star, the solution is in less than delta, right? It stays inside that ball. At t star, it touches the boundary, and after t star, it just flows out. That's what we are saying. So basically, flows outer. Okay. So you see, for t less than t star, what happens is this term. Okay. Satisfies this particular thing. You see, we can actually bound it. So basically what we can do is this, the second term satisfies k times 0 to t e power epsilon s r of xs ds. Okay, this is dominated by k times eta 0 to t e power epsilon s mod xs ds, okay, which is nothing but k times eta 0 to t g of s ds. I hope this is clear. Okay, is it fine? I'm just writing this part there. Okay, see this particular second expression. Yeah, okay. Now we use Gronwall. Huh? So now if we use Gronwall, by Gronwall, what happens is Gronwall lemma, we have that g of t in this case will be less than equal k mod b e to the power k eta t, okay, for all 0 less than equal t less than equal t star. Okay, now if you just look at what is g of t is e power epsilon. See, what is g of t? E power epsilon t mod x of t. So therefore what you have is therefore mod x of t, or norm of x of t, I should not say mod, it is norm of x of t in this case, is e power minus epsilon t g of t. Yes, now if we put everything together, it is less than equal k times mod b e power k epsilon k eta minus epsilon t. That's what we have, right? So see, now the exponential is decaying, right? See, why we choose, see, k eta minus epsilon, if you look at this, you see k eta minus epsilon is negative. Okay, so as time tends to t tends to infinity, what is happening is this particular thing goes to 0. Exponential, this particular thing goes to 0. Okay, so what is happening is this, so the solution never leaves the ball of radius delta, right, as t tends to infinity. Is it okay? See, if this is true, then this can be made less than delta, right? That's what we see. This is small, as t tends to infinity, this is small, so we can write it like it is less than k times this. Okay, once again, let me just I should put it in proper. Okay, so okay, fine, let me put it this way. See, norm xt is this, right? And now the exponential is decaying, k eta minus epsilon, that goes to, that is negative, right? That we know. Therefore what do we have is this norm of x t star, let's say, if we take t star, okay, so that will be less than k mod b. Yeah, if you look at it, it will be, because this is going to 0, right, as t tends to infinity. Okay, so you can make it less than k times mod b. Okay, and what is k times mod b? This is less than delta. That is our assumption, right? Okay, so that's a contradiction, because k x of t star, we are saying that this is equals to delta. You see, x of t star is equals to delta. So that's a contradiction. Okay, so what does it say? It says that I mean, if you have a solution which is trapped, okay, if it's not trapped, so basically if it leaves the ball, then there is a contradiction. So basically what we proved is, if there is a solution which starts in a neighborhood of b star, it stays there. Okay, and for all time t, it is actually, defined, and it stays in a neighborhood. Okay, and what happens is, since you see this is true, x of t is less than k times mod b e power k eta minus epsilon times t, and k eta minus epsilon, this is negative, right? So as t tends to infinity, norm of xt must goes to 0. Okay, and 0 is the equilibrium point. So basically it says that it is asymptotically stable. Is it okay? So that's how you prove this theorem. Is it okay? Now the thing is this, what I want you to do is this, see, the theorem is quite clear. Okay, now let's look at the Duffing's equation. Okay, so consider this equation now. So this is an example. Okay, I am not going to do this thing, you have to do it. So for x prime equals to y, and y prime equals to x minus xs cube minus beta y. Okay, we have seen that 0 0 and plus minus 1 0 are the equilibrium points, right? Okay, so what we need to do is, that plus minus 1 0, okay, these are asymptotically stable. Okay, so this system are asymptotically stable near these points. Okay, so you please check this. What do? You see what is f of xy in this case? It is nothing but x, y, and x minus x cube minus beta y. Just find out what is df and what is the b star here, plus minus 0. Find out what is that. Okay, once you do it, you can talk about the eigenvalues of df plus minus 1 0, right? Talk about the eigenvalues, write down the eigenvalues. If the real part of those eigenvalues are negative, then you know that you can actually use this theorem to say conclude the asymptotic stability. Is it okay? So you have to check this part yourself. So please do it yourself. And with this, I am going to end this video.